Okay, chapter 5. We have 6 sections, possibly 5. I'm going to look into that if we need to do all 6 or if we only have to go through 5. This week, remember, I won't be here Friday. How many of you seniors going on the trip? Anybody? So, we have the senior snow tubing trip Friday, so what I plan to leave on Friday is, just the note that y'all are working on your My Math Lab. I'm not planning to flip the classroom Friday, but I will let you know if that changes. If it's something short, sweet, and very simple, I may flip the classroom. If not, then it would be y'all work on your My Math Lab on Friday. The sub is Miss Pennington.
Yes!
Here's
Suzanne.
Here's
Suzanne.
Okay. That's fine.
Dude, Miss Pennington.
No, she's not.
Our teacher is coach.
All right. Chapter 5. We're looking at exponential logarithmic functions. This is, if you went through Algebra 2, you may remember exponential and logarithmic functions.
God, I hate logs.
That's great. And we are, hopefully, I'm going to teach you a technique.
Laggy tail.
Hey, but like if you get
That's
you
right.
can like build sky
I'm going
eggs
to
and
teach
like-
it in a more mature fashion that hopefully...
Taylor.
I'm going to show you
Great
a
day to
technique.
be alive, baby.
I don't know for the
You could create 2 90s with one.
You do. You do need this for the ACT, so pay attention. All right.
Tell better lock in, no. You better lock in.
Open
21?
your notes
Alcohol?
to this slide right here. Okay. If I've said it once, I've said it 1,000 times. When you're learning math,
He's on top of the mansion.
when you're learning math, in order to understand something complicated, dial it down to an elementary foundational level. Because then, if you can understand that, you can build up to the more complicated problem, okay? Always, always bring it down simple. So we're going to start simple. We're talking about what are inverse functions. You've already practiced with this before. What is the inverse of a quadratic? X squared. The inverse would be the opposite, which is square root, which is the square root graph. Okay, but now we're looking at inverses of exponential functions and logarithmic functions. We're going to start simple. Instead of looking at a graph or an actual equation, I want you to focus on just this set right here. We have the set H. It consists of these coordinate points. We have 4 coordinate points. This is what the inverse of set H would look like. It says inverse of H. Look at the 4 coordinate points. Look at the original. What do you notice happened? What? Be specific. The X and the Y's flipped positions. They switched. Do you see that? Within each point. The inverse relation, this was just a relation, not an actual graph. So the inverse relation is to just take the X and Y coordinates and switch them, which is what happened here. So come right here. We've got set G. Consider the relation set G. Tell me what the inverse would be. What is the inverse of G? Tell me the inverse of G. I'm sorry, rhetorically. Write it. How's that?
There you go.
Is there a fancy letter for the inverse of G?
There is. It's a symbol. I'm gonna show it to you. All right. So what'd you get as the inverse set? 4, 2, 3, negative 1, and 0, negative 2. The notation for inverse is a little -1 right here up in what looks like an exponent's position, it is not the -1 exponent to say, hey, grab the base, grab the exponent, and move it. It is not that. It's just a notation. So this is the notation for inverse. Alright, so now what does it look like in terms of graphing it? So in this box over to the right, I want you to just sketch an X and a Y axis right in the middle. Sketch an X and a Y. And then, let's see, we stayed within 4 coordinate points. So do 4 tick marks to the right, up, left, and down. Do 4 tick marks. To the right, to the left, going up, and going down. And I want you to plot those points. Do me a favor and plot one set in bold and the other set maybe in a smaller dot so that you can see the difference between the two. So you're plotting 2, 4, -1, 3, -2, 0, maybe in a light point, and then you're plotting your inverse set in a bold dot. And did yours look like mine? Kind of. You've got 3 here, here, and here, and then 3 here. Now I would like you to sketch a dotted line that is running diagonal from top right. Okay, I'll have as I try to sketch mine, my picture disappears. So just look at mine. Sketch a diagonal line from top right to bottom left. That dotted line is the line of symmetry with the first set and the inverse set. You should notice that if you were to fold the paper along that dotted line, these points would match up. It would almost be like if you had wet ink on one side, you folded the paper, you opened it up, and then it plotted the other side. That line of symmetry is important when it comes to inverses. Anytime you have 2 inverse functions on the same graph, you should notice a symmetry about that diagonal line if you were to fold it. So let's call this the line of symmetry.
I'm gonna need a bigger scale.
Okay, so this slide practiced it when you have just points, relations. This slide is practicing it when you have an equation. Notice it's not a function because it says y. It does not say f of x. So this is just an equation. What do you think is going to happen in the equation? What happened in the points? Be specific. X and y switched. So what do you think we do in the equation? Switch x and y. All right, so look at this equation we have right here. We are going to switch x and y. Are you okay? I'm going to bring down the rest. You'll notice that I tried to color coordinate it so that you could see. So everywhere there was an x, I wrote a y. Everywhere there was a y, I wrote an x.
Okay, now.
Sometimes you can get y by itself and actually see the equation. In this case, we have 2 y's. We don't want to try to get y by itself. It would be a headache. In this case, you could just leave it as is, and you would say that this is the inverse of the given equation. Now, in terms of graphing it, let's try to keep it simple. I just did a T-chart, so I'm going to show you. I want you to start over here. Start over here, I'm going to put a 1. I did a T-chart. I picked some numbers for X. I plugged them into the original equation, and I got the values for Y. Okay, and then I graphed it. Notice this is color coordinated, so you will notice this is the blue quadratic that you see here. So this is graph 1. In terms of the inverse, because the inverse was ugly, like normally we pick numbers for X and plug them in to get Y, right? Well, we have 2 Y's, so we've got to go about it backwards. So let's pick numbers for Y, plug them in, and see what it gives us for X. So that's why the T-chart looks different over here in this one. I picked numbers for Y, I plugged them in, and I found out what I got for X. And then I graphed it. Okay? So I'm going to give you a few minutes to kind of jot that down, just to help you understand, wrapping your mind around what we're doing here. The T-chart is -1, 0, 2, and 4 for X. My Y values were 6, 0, -6, and -4. And my Y values over here, I kept the same numbers, this time I plugged them in for Y. When you plug them in, I came out with these X values. What do you notice about the 2 T-charts?
The inverse?
Yeah. So remember what we just did with the coordinate points, the same thing happens in a T-chart. So, yeah. You just, right. Well, you're going to do it on this slide, but then from here on out, you don't have to. Yeah, so 1 T-chart would suffice. You would just have to really think hard when you go to graph the second one. You'd have to look at the Y column and use that as your, like telling yourself, okay, I'm plugging these in and this is what I get. And like we said, this was not a function, this was just an equation, because what's wrong with the red graph?
It's sideways.
It is sideways, and it definitely fails the
Function.
both right. It fails the vertical line test, which is the test of whether or not it's a function, which I hope you remember because it is coming up again with another purpose. Is anyone still writing?
Yes.
Okay. Not a problem.
Do you have iron yet? You smiling?
Oh, I'm good.
Oh, what?
I just play outside.
He's playing outside right now. He's in Minecraft.
Actually, he's in region.
He's in the
Brody, did you finish?
Yes, ma'am.
Okay. Is everyone else finished? Y'all good? Writing that down? Okay.
Is you sending up to this?
I have a picture. No, you're good.
Okay. So the point of this slide is to show you how to find the inverse when it's an equation, and then seeing the graphical representation of the inverse. Notice that dotted line right there of symmetry. Also understanding that if I give you the t-chart for a function, you can just take them and swap them, graph it, and now you have the inverse, okay? Look at this slide right here.
That looked dumb.
So we have two relations. These are called relations,
Oh, I hate these.
where they're not everybody's favorite. You have to really think about it.
When do I get
Where-
the logs?
Where you're saying to yourself, in the year 2006, the cost of a stamp was 39 cents. In the year 2007, the cost of a stamp was 41 cents. In the year 2008, it was 42. Okay, for 3 years after that, it stayed at 44 cents. Then you can see how it progresses. Now I think it's like 60. I don't know. I buy forever stamps every time because it always keeps going up. This is a relation showing you that for each calendar year, there was assigned one cost of stamps. Now, the cost could be repeated, but the calendar year did not get repeated, right? Okay, what if I reverse the arrows?
Then it's not a function.
Now, it'd be hard for you to reverse them on your paper. I get that. Look at mine. I just reversed the arrows. It was like magic. Is it a function? No. Why not? This is a problem,
49.
and this is a problem. This is like trying to graph, imagine plotting, right 44, up 2009, up 2010, up 2011. You would be like, okay, now which is it? You know, I went right 44, but now where do I put the point? This would be like saying go right 49, but then I'm not sure if you're going to put one at 2014 or 2015 or both. So this is why it fails the function test, okay? An input, which is your X column, right here, has been repeated, which fails the vertical line test, which fails the function test. So let's take notes underneath it. Not, well, you should write this. Because on your paper, you have the original, you don't have the inverse. So let's make a note. The inverse is not a function. And the problem, we said, was 44 and 49, so I put an X next to those.
Can we write down Y on the, so I can remember this.
Yeah, you can circle if you want, and you can make a note, draw an arrow right here. Now, you have to remember that it's, watch the graph as it changes. That's the one I'm thinking of. You with me? That's the one where I flipped the arrows, not this one.
So maybe write inverse wrong.
So we've said the inverse is not a function, and it's because these values repeat. It had repeated input values when you flip the arrow. But I'm going to show you a trick to this in just a second. Now come to this one right here. These are just random numbers, random y values. Oh, the cube. They cubed it. Is it a function this way?
Yes.
Yes. Magic trick.
Yes.
It's still a function, right? So let's make a note. The inverse is a function. What is the difference between the first picture, which was not a function, and the second picture, which is a function?
Only one value is assigned.
There you go. Hence the vocab word one-to-one. One-to-one, meaning you could think of it as a ratio. It's saying, hey, for every one x value, it goes to exactly one y value, and they don't repeat. So this is a 1-to-1 function. When you have a 1-to-1 function, you can automatically say that the invert, now you have to really follow what I'm saying, because I'm going from the function, which means the one you started with, then I'm going to the inverse. So stay with me. If you have a 1-to-1 function, then its inverse is by default also a function because of the 1-to-1 properties. All right, so find some room on your paper, and I want you to write this. I don't really have any room, but we're going to summarize maybe in the gap in between the next slide or over to the far right. If a function, and I'm going to abbreviate function with f of x, and I'm abbreviating 1-to-1 to look like that. If a function is 1-to-1, then its inverse is also a function. Spell it right. So if a function is 1-to-1, then its inverse is also a function. So if f of x is 1-to-1, then the inverse passes the horizontal line test. Does that make sense? So we're talking about two totally different functions here. That's where some people get lost. But we're saying if your starting function is 1-to-1, then without even having to check it, I can tell you, okay, well, its inverse will pass the horizontal line test, meaning it will be a function as well. And that's because of that 1-to-1 relationship. You don't have to worry about arrows getting repeated because it was 1-to-1. You know what I mean? It's almost like train tracks when you draw the arrows out. Okay, go to this slide. This slide gives you the formal definition of 1-to-1. It's very fancy. College level is saying that if a function is 1-to-1, let me explain how to read this. Then if you take two numbers, A and B, that are not equal, that's why I said A and B, not A and A, they're not equal, and you plug them into the function, you will get two totally different answers. So I'll read it again. If you take two numbers not equal, plug them into the same function, and you'll get two totally different answers, it means the function is 1-to-1. So coming over here, it'd be like if I plugged in -3, I got -27. Then I plugged in -2, I got -8. My input values did not equal each other. My output values do not equal each other. So there, that passes the function 1-to-1 test. Okay? Another way to say it, look, notice it says or, meaning, there's another way to look at it. If you have two outputs that are equal, but they come from two different inputs, that's another test for 1-to-1. I don't expect you to understand it from that right there. We're going to practice it on the next slide, so give me a second to maybe absorb what I just said, and then we'll come back to it and I'll say, do you get it now? By the way, here's where I am reminding you of the notation for inverse. It's the little -1. Don't misinterpret that as the -1 exponent that tells you to move it to the bottom. That is not the case. All right, so come down here and look at this box. This box is summarizing everything we just said, and then it's giving you a couple of new parts. When you have these equations, the x and the y swap, right? Okay, well then what happens with the domain and the range? So the domain and the range, there's a relationship with them as well. Because remember, in the T-chart, domain was your X values, range was your Y values. So the domain, the X, of a one-to-one function matches the range of its inverse. Well, that goes right back to over here when we said, notice these T-charts match. Notice that where's the original? The domain here, the input, matches the range here. You with me? And then the output, the range of this equation matches the input over here of its inverse. So they're linked together. All right, go to the next slide. Let's get to the algebra behind it. You ready? We're going to practice two of these right here. Example 3. Given that the function f described by f of x equals 2x minus 3, it says prove f is 1 to 1. If we're proving it's 1 to 1, we're saying that its inverse is a function. We have two ways we can prove it. We have method 1 or method 2. I personally find method 2 easier because method 1 only takes care of two cases. Method 2 is kind of like proving by contradiction. So let's copy this right here. Copy that down, and then I'm going to explain what we're going to do. You're going to work on the left side, work on the right side. You're plugging A into the function and writing it over here. You're plugging B into the function and writing it over here. What is the function? It's right here. 2x minus 3. So if I plug A in, I would have 2a minus 3. Right? Now plug B in. What do I get? Actually, it's 2b or not to be. Now that you have those values plugged in, you are free to work on this with the rules of math. Whatever you do to one side, do to the other. And the goal is, can we get down to A equals B? So the first thing I see is I could add 3 to both sides, right? And if I do that, it's just going to disappear. So I'm going to show that I'm adding 3 so that you know why it disappears. The next thing I see I can do is what? Divide both sides by 2. And I end up with A equals B. I'm going to go back a slide real quick. I know you're writing. Notice here it said, if you start out with f of A equals f of B, and you can get it to A equals B, then the function was 1 to 1. Which means its inverse is also a function. Have you ever seen this before? This is shorthand notation for saying like therefore, put in, all right, everything I sometimes do an arrow. So if you don't like the 3 dots, you could just do like what I've done before, saying like, all right, I just did all that and now I'm putting my thoughts together. If f of A equals f of B, then A equals B. So f of x is 1 to 1 here. We took f of A equals f of B, we manipulated them following the rules of math, and we came down to A equals B, which means that this function is a 1 to 1 function, which makes sense, it's linear, right? All lines should be 1 to 1, because The input changes, the y changes, the input and y. That's the slope behind it, right? Alright, let's try this one. Given the function g described by g of x equals x squared, prove that g is not. It's telling you straight up, hey, by the way, you're going to come to the answer here that it is not 1 to 1. So let's start it again. We've got f of a equals f of b. Plug a in, plug b in. Okay, what am I allowed to do? Square root both sides, but what do I need to remember? When I'm solving and I square root, there you go. And now that's where the problem comes from. Now, if you don't see it, let's look at a counterexample. Meaning, if you can come up with one single example that it does not work, then that's your counterexample. And you've proven that, hey, no, it's not 1 to 1. The counterexample would be, let A equal 3 and B equal negative 3. If I plug 3 into x squared, what do I get? 9. So f of 3 would be 9, correct? If I plug negative 3, plug it in, to x squared, I would get what? 9. So f of negative 3 would also be 9, correct? So were they equal? Okay, but did A equal B? Look right here. No. So that's the problem. My outputs both came to 9, but my inputs were two totally different numbers. If you go back over here and look at this, they had to be consistent. It's either your inputs don't match and your outputs don't match, or your outputs match because your inputs matched, right? Where it says A equals B, they're saying, hey, those two numbers you started with that we said assume they're different, they actually resulted in the same number. So right here, we can make a note that A did not equal B, but we found that them both to come to 9, so that's a problem. So no, in this case, g of x is not 1 to 1. Now, what does it look like in terms of a graph? And y'all can just sketch this. You don't have to write all this down. You could do 3 little graphs, and you could, or actually, let's see, you could just do this one right here. This first graph. The blue and the red are showing you two functions. This is not specifically x squared. X squared would actually look like this. X squared would be this way, and the inverse would be that way. And the inverse definitely fails the vertical line test, right? So this is just showing you another function. But notice if I take blue, reflect it over the dotted line, I end up with red. Red is not a function. Red fails the vertical line test. So this is an example of what that would look like in terms of a graph. Which brings us to, now the vertical line test is called the horizontal line test.
I think we'll take a very quick 2-minute bathroom break.
Maybe.
I need to get up and stand up. I need to stand up.
Okay, go to this slide. There are 4 graphs here, and I'm learning you. You better take that AirPod out. I'm teaching you what's called the horizontal line test. It's the exact same concept as the vertical line test. Wait for it.
But vertical.
But it runs horizontal.
No, more.
Now it does test for something different. The vertical line tests if a graph is a function. You with me? The horizontal line test, follow me here, runs on a function to tell you if its inverse graph would pass the vertical line test. Yeah, alright, I'm going to do it again. So, the horizontal line test, you run on a function, and if it passes it, then that's telling you that the inverse function graph would pass the vertical line test. So there's a lot, it's a mouthful here to understand that if I'm running the horizontal line test on the original function, I'm answering a question about its inverse passing the vertical line test, which would mean it is a function. Okay? This is the faster way to check without having to do, what was it? This. Without having to do this, you could do this. This is the algebraic way to check it. Or if they don't actually tell you what the function is, this is the faster way to check it. So, example A. The function is 4 minus x. Does it pass the horizontal line test? Yes. If I if I draw a horizontal line anywhere on that graph, it's only intersecting in how many spots? 1. That means it passes. What's the question actually asked? From the graph shown in each of these, determine whether the function is 1-to-1, which tells you that the inverse is a function. So yes, this is 1-to-1. I would like you to do B, C, and D. Okay, what'd you get for B?
No.
Definitely not. In this particular example right here is a random horizontal line, and it's crossing in 2 spots, so it is failing the H test. Which means if I take that graph, reflect it over the dotted line, and then try to drop a vertical line, it would fail it as well. Okay? So maybe that's another way to make the connection. If it passes the H test, its inverse passes the V test. If it fails the H test, its inverse would fail the V test. You with me? What about C?
I said yes.
It is. Just because it's going almost in the same direction, it's still gradually, going up. It's not touching in more than one spot. What about D?
Flattened out.
Definitely not.
What if it flattened out? See?
It's still okay.
Just because it's
Yeah, it's just still gradual. That's actually the cubic function. So the inverse of the cubic would be the cube root. So there is a gradual change. You just can't see it. Also, we would never get that nitpicky.
610.
All right. So the horizontal line test is a beautiful thing. It tells you the fast way of saying whether a function's inverse is a function. Now, well, that's to make you appreciate the algebraic way. Now, let's go to, okay, we have a function. We already know its inverse is a function. Now let's get to the algebra behind finding the equation of its inverse. Okay? So now we're no longer answering the question, does it have an inverse that is a function? Now we're saying, hey, here's the function. tell me its inverse. It goes back to what we've already done. It's as simple as the x and the y's swap, right? The difference is f of x is your y, and at the end, your y needs to be replaced with the notation to say f inverse of x. That's the difference. And we are solving for y this time, every time. Okay, so let's look at this one. We've got f of x equals 2x minus 3. Notice it says determine whether the function is 1-to-1. Okay, well, we've already done it in the algebraic way. We did it with f of a equals f of b. We added 3, we divided by 2, we came to a must equal b. Let's think about it the graphical way. If I'm trying to answer the question, is it 1-to-1? Think of the graph. 2x minus 3. What is that?
Linear.
It's linear. It's, remember the phrase, begin with b, move with m. It's at -1 to right here, and it's going up to right 1, up to right 1. So it's like that. Is that going to pass the horizontal line test? Yes. So it will pass the H test. Therefore, f of x is 1-to-1. The next part's the new part. It says find a formula, which means tell me the equation for the inverse. You get this by changing f of x to y, swap x and y, solve for y, rewrite it with the fancy notation. So I'm going to copy the whole function right here. Are you able to see? Getting out of the way around this. I'm going to change this to y. Now I'm going to swap them. Now I'm going to solve for y. So I'm going to add 3 to the left. And then do what? Divide the whole thing by 2. Right? Since we're just trying to get the equation, you don't have to go underneath each thing. We're not graphing it. We're just trying to get the equation. So the inverse is x plus 3 over 2. Yep.
I just want to make sure she's okay with that.
All right, go to this slide. What do you notice about these two functions? Yeah, they look familiar, don't they? Let's graph them on the same graph. So come to this box, draw an x and a y coordinate plane. I would do tick marks, 5 out, 5 up, 5 left, and 5 down.
Yes. I'm doing your work.
So draw an x and a y axis and do 5 out in all 4 directions. We are going to graph these on the same line. Let's graph one of them bold and one of them, not so bold. Or you could do the one regular and the other one dotted. I don't know. It's up to you. Actually, I'd rather you not do the dotted now that I think about it. So we're going to do the line of symmetry. So we're going to graph f of x equals 2x minus 3. Remember, begin with b, move with m. Right? So on your line, you've got -3, and you're going to go up to right 1, put a point, up to right 1, put a point, and then you're going to draw your line. Now we're going to graph the inverse. Earlier, we said you can just write the whole thing over 2 because we were not graphing it on that slide. Well, now we're graphing it. It's hard to graph x plus 3 all over 2. So let's divide each individual thing by 2 so we can actually see what these numbers are. This is a 1/2 x plus, and then what's 3 divided by 2 as a decimal? 1.5, right? 1.5. So if you need to know where I got that 1.5 from, I just did 3 divided by 2 as a decimal, because I could graph that. If you need to see it like this. So, begin with B, 1.5, move with M, rise 1, run 2. So 1.5, then rise 1, run 2. And now that I've done mine crooked, I'm going to reveal the answer. There you go. So you can see the 1.5's right here, and then it's really hard to see. Rise 1, run 2. Rise 1, run 2. Once again, the dotted line, which is the line of symmetry, is where you would fold that and those would match, right? By the way, the equation for the line of symmetry is y equals x, which is kind of cool because how do I find the inverse of the function? Yeah, you switch the x and the y's. So the relationship is that they reflect over the line of symmetry y equals x because you literally switched x and y to find it. All right, go to the next slide. Did I leave that on there? Oh no, I left the original. Okay, good.
Carmelo Anthony?
Chris Bosh.
Probably.
Kawhi.
Consider g of x equals x cubed plus 2.
Joel Embiid.
Says determine whether if it's 1 to 1. If it is 1 to 1, what's the formula for its inverse, and then graph it. Okay, I've given you the graph of the function. So we can answer A real quick. Is it 1 to 1?
Yeah.
Why? Okay, so let's say passes H test. And we'll draw an arrow to say, okay, so therefore, yes, it's 1 to 1.
Thank you!
Thank you.
Hopefully you remember what the H test is, horizontal line test. Since it is 1 to 1, that means you can find its inverse.
Thank you!
This would be where you take X and Y and you do what with them?
Switcheroo.
Switch them and then solve for Y. I'm going to go ahead and say that this is Y. So I'm going to go ahead and switch them so I have less writing. Alright, what do I need to do first? Subtract the 2. What is the opposite of cube? Cube root. So I'm going to cube root both sides. When I cube root the right, it will just become a y. And then of course you're supposed to change that to F inverse, or is it F? G. G inverse is the cube root of x minus 2. Now it says to graph it. Let's think smarter, not harder. Let's don't be complicated here. You already have the function g on your paper with 3 coordinate points listed for you. What was the very first thing we did when finding the inverse?
Plot the x and y.
Thank you. So please go to your picture. Instead of graphing 2, 10, you're going to plot 10, 2. Then you're going to plot 2, 0, and then plot negative 6, negative 2. And then do your best to draw a curve. It is a curve, it's not a straight line. Here's what it's going to look like in red. So plot those 3 points, but plot the opposite of them. And then just try to draw kind of a smooth S kind of through them. Alright, are you good? Go to the next slide. What if I give you 2 functions and I want you to tell me, are they inverses or not? Well, there's an algebraic way to do that. The algebraic way is 2 steps. You have to have 2 steps. First, second. You're going to, y'all remember function composition? Write the first function, beat the x out, plug the second function in. Remember that? Yes. You're going to do it twice because order matters. So you do it in one direction, then you do it in the other direction. And the goal is right here. This is the goal. That it cleans up to be just x. If it cleans up to be just x, meaning stuff cancels out, and then you do it the other direction and you get x as well, it means the 2 functions are inverses of each other. Okay, so here's what it looks like. We've got f of x equals 5x plus 8. You probably can already see where this is going. That's definitely linear. This is also linear. We've got x minus 8 all over 5. We're going to confirm that they're inverses. We have to do it 2 ways. F of f inverse. And then, now depending on how big you write, you can write that here, then come over here, or I'm going to come down here. I'm going to do f inverse of f. So you have to show both directions. Now, here's your refresher on how to do this. Order matters. You're going to write the first function first, so 5x plus 8, and as you write it, you're going to do what?
Beep out the x.
Beep out the x. So 5 beep plus 8. In the beep, you're going to put,
X plus 0.
there you go. Now, I like to write it where it's level with the number, like that 5 is understood to be over 1. So I'm going to write the x minus 8 level with that. And you can see why, because as I clean it up, what happens immediately? The 5's definitely cancel immediately. And you're left with x minus 8 plus 8, and what happens there? Those cancel, and you're left with x. So that direction checked out. Now we've got to do the other direction. Write the first function first, as you write it, beep the x out. So beep, minus 8 all over 5. What goes in the beep? Yep.
8's cancel.
There you go.
It's plus 8.
Oh, I wrote minus 8. Thank you. So what happens across the top?
The other one is plus 8.
I mean, it wouldn't matter.
Right.
technically, but It's the other one.
Oh, thank you. What happens across the top?
8's cancel.
And I'm left with,
5x over 5, 5's cancel.
there you go. I've run out of room.
Equals
I'll
X.
try and write right there.
So yes, it checks out.
Yes. There is one slide left. The extra stuff that's on there was pictures I was trying to give you to help with understanding domain and range. This slide that's talking about restricting the domain, I'll show you this real quick and we can put the notes on your paper tomorrow. This was just saying sometimes you can take a function that does fail the H test, but you could restrict it and then it would pass the vertical line test. So it is possible to take the ones that don't work and say, okay, I'm just going to look at these x values and then it would work.